Now we will continue our discussion of normal modes of the one-dimensional monatomic Bravais lattice. So last time we have talked about the periodic boundary conditions, Born-von Karman periodic boundary conditions. So the zeroth atom and capital N atom displacements should be the same. And we have also obtained the equation of motion from basically Hooke's law, considering the springs between two atoms. Now, the solutions we will look for are traveling wave solutions. They are of the form A amplitude times exponential I k wave vector dot product with position vector of the atoms Rn, the equilibrium position vectors, minus omega t. So if you remember A cosine kx minus omega t or A sine kx minus omega t in one dimension, that was the traveling wave solution from fundamental physics classes, and this is just a generalization for three-dimensional space. Now we can substitute for the positions of the atoms n times a. A is our lattice constant, so this is our equilibrium atomic position. Now when we substitute for Rn, n times a, and if the wave vector is parallel to the position vector, so let's see if that's the case. So we have a wave that will propagate in this direction. So we're talking about a longitudinal wave here, for example. Therefore, you can see that the position vectors for the equilibrium positions will be parallel to the k wave vector. So this is basically one position vector here, r n minus 1, for example, for the n minus 1 atom. So if I take this as a reference point here, that would be the position. So this would be origin, for example. Okay, so we have these solutions a e to the I, k, and a, because they are parallel, minus omega t. So these solutions we are looking for represent a traveling wave. So it's a traveling wave in which all atoms oscillate with the same frequency omega, angular frequency omega, and amplitude a, and we have a single wave vector k. Now, why is this solution possible? Because we have translational symmetry in the crystal. The solution is of this form is possible. Now we're using Born-von Karman periodic boundary conditions. We set the zeroth atom displacement and capital N atom displacements to be equal. For the zeroth atom, we have capital A e to the minus I omega t. For the capital N atom, e to the I k capital N a e to the minus I omega t. So that basically will imply e to the I k N a is equal to 1. So our wave vector magnitude is 2 pi n divided by capital N a. So n is an integer. It takes values from 0 to capital N minus 1. So it has capital N distinct values. So we're counting the atoms starting from 0 to the n minus 1 atom. And capital N atom and 0th atom are the same because we're using periodic boundary conditions. Okay, so this has some discrete values. Now, you can see that there is a phase difference between the motions of each atom, and the phases are interlocked such that the phase increases regularly from atom to atom by Ka. So what do we mean by that? If you go from the nth atom to the n plus 1th atom, so if you write the ratio of the displacement of the n plus 1th atom to the nth atom, what would you see? You would see that this ratio would be equal to e to the I capital K n capital K a. So from n plus 1 to n. So we would see that this phase is increasing regularly from atom to atom by an amount Ka. So the phase increases regularly by an amount Ka. Okay, and now if I substitute this solution into the equation of motion, I will find omega versus k relationship. So for that, I go back to the equation of motion. The equation of motion I obtained was this. ma, md square u and dt square is equal to the spring constant c, m plus 1th atom displacement plus n minus 1th atom displacement minus twice nth atom displacement from equilibrium. So I need the first derivative. So the first derivative, time derivative, will give me minus I omega times un, and the second time derivative will give me minus omega I omega squared. So minus I omega squared is I squared omega squared, which is minus omega squared un. So from the equation of motion, we will get capital M d square u and dt square becomes minus capital M omega square un, and the right hand side, the displacements times the spring constant c un plus 1 plus un minus 1 minus 2 un. Okay, so I substitute for un basically the solution that I'm suggesting, the traveling wave solution, minus m omega square a e to the I k and a e to the minus I omega t. And then I have in each term here e to the minus I omega t, so I take that out, and also the amplitude c times a times e to the minus I omega t, e to the I k n plus 1a, e to the I k n minus 1a, minus 2 e to the I k n a. So first of all, I notice that a e to the minus I omega t's will cancel, and then I want to divide this equation by minus e to the I k n a. Okay, so if I divide it by minus e to the I k n a, you can see that the left hand side will become just capital M omega square. And the right hand side, c times, I had minus 2 e to the I k n a, that will become plus 2. And then I had e to the I k n plus 1a, so that will become e to the I k a with a minus sign. And then I will have e to the minus I k a with a minus sign. So now what is e to the I k a? What is e to the minus I k a? Well, there I need to know Euler's formula. So e to the I k a is cosine ka plus I sine ka, and for e to the minus I k a, I have cosine ka minus I sine ka. So I substitute that here, 2 minus cosine ka minus I sine ka, and then with a minus sign here, minus cosine ka minus I sine ka becomes plus I sine ka. So you can see that I sine ka's will cancel. So c times 2 parentheses 1 minus cosine ka is what we get. And from cosine ka we can go to using our relationship between sine ka over 2 and cosine ka from trigonometry. Cosine ka is 1 minus 2 sine square ka over 2. So I substitute that here. 1 minus 1 plus 2 sine square ka over 2. Ones cancel. So I obtain 4c sine square ka over 2. And the left hand side was capital M omega square. Okay, so omega becomes square root 4c over m. And then I have to take the square root of sine square ka over 2. And omega must be positive, so a sine is an oscillating function, it can have negative values. I have to guarantee that omega is always positive, so I put an absolute value. So square root 4c over m, absolute value sine k over 2. Now this relationship that we obtain, omega versus k relationship, this is known as the dispersion relation. It's an important relation, and it tells us the nature of the oscillations. Now, I noticed that this function sine ka over 2, if I put here k plus 2n pi over a, I obtain sine ka over 2 plus n pi, that will become sine k over 2 cosine n pi plus cosine k over 2 sine n pi. Sine n pi is 0, so cosine n pi is plus or minus 1 because I have absolute value becomes sine ka over 2. So basically I see that the angular frequency omega and the displacement un are both periodic with a period 2 pi over a. So angular frequency omega is periodic, displacement is periodic with a period 2 pi over a. So 2 pi over a is something special that I remember. If a is the lattice constant, direct lattice, for example, the simple cubic lattice, then the reciprocal lattice constant is 2 pi over a. So the midpoints of the shortest reciprocal lattice vectors, plus or minus pi over a, define the boundaries of the first Brillouin zone. So this is what we discussed in the X-ray diffraction. So what is our conclusion? Therefore, we find that because we have periodicity 2 pi over a, the distinct values of k will be in the range minus pi over a to plus pi over a. So that's called reduction to the first Brillouin zone, because after that point we have for the other Brillouin zones the same thing repeating itself. So omega is square root 4c over m absolute value sine ka over 2. What is the maximum value of this? Well, absolute value of sine ka over 2 will have a maximum value 1. So we will have 2 square root c over m is the maximum angular frequency. So omega divided by omega maximum is sine ka over 2 absolute value. So if I plot this between minus pi over a and plus pi over a, I see this basically half a sine between 0 and plus or minus pi over a. So if I have a long wavelength, so k is equal to 2 pi over lambda, k goes to 0, you will see that I have this long wavelength limit. So it's becoming a linear relationship between omega versus k. That's graphically what I observe. So another thing I observe is that omega of k and omega of minus k are the same. So this curve is symmetric. So a mode that is traveling to the right has the same frequency with one traveling to the left. And the two directions are equivalent. There is no preference. Now, if I look at the first Brillouin zone boundaries, and if I substitute k is equal to pi over a, for example here, a e to the I k n a, for k I substitute pi over a, e to the I pi n minus omega t, and that's a e to the I pi n cosine pi n plus I sine pi n. So sine pi n is 0. So this will give me cosine pi n, which is minus 1 to the power n. So depending on the value of n, this could be minus 1 or plus 1. E to the minus I omega t. So this is not a traveling wave anymore. What is this? This is a standing wave. So it's a standing wave solution. From fundamental physics, remember we have a sine kx cosine omega t, for example, that is a standing wave. We have nodes and antinodes in the standing wave. So this is just an oscillation in time. There is no oscillation in space here. So a e to the parenthesis minus 1 to n e to the minus I omega t, that gives me a time oscillation. So that is a standing wave. So this represents a standing wave, and atoms with even and odd n values will oscillate with opposite phases because the phase is changing with this factor minus 1 to the power n. So there's something interesting going on here if you consider the Bragg reflection of X-rays. So now we're talking about elastic waves, but the wave behavior should be similar. So if I consider Bragg reflection, Bragg condition, remember, is 2d sine theta equals n lambda. So d was the distance between two neighboring planes, and lambda is our wavelength, and theta is the angle of incidence. So we have lambda is equal to 2 pi over k, the wave vector, and k at the first Brillouin zone boundary is pi over a. So 2 pi divided by pi over a becomes 2a. So when the wavelength is equal to 2a, and the distance between the two planes is equal to one lattice constant a, I find that n must be equal to n is equal to 1, gives me sine theta is equal to 1, which means theta is pi over 2. So basically this is our one-dimensional lattice of atoms. You have the k vector that is traveling to the right at an angle pi over 2 with respect to the normal to the plane of atoms, and you can see that this condition is satisfied to give a Bragg reflection condition, constructive interference, when k is equal to pi over a. So all the scattered waves will interfere constructively and standing waves will be set up. So in the propagation of elastic waves, we have a special situation when k is equal to pi over a or minus pi over a. It's the first Brillouin zone boundary. We have constructive interference and standing waves will be set up. So theta is equal to pi over 2 also makes sense because elastic waves will only have a meaning at the atomic planes and not in the space between them. So you cannot have an elastic wave that is coming at an angle like this. So this is not possible. So you have the elastic wave will propagate on this plane of atoms in this manner. Now, in the long wavelength limit, when lambda is much greater than a, what will happen to k? Well, k is equal to 2 pi over lambda. 2 pi over lambda goes to 0. So k times a will be much less than 1. So let's look at this limit. Our dispersion relation omega versus k gives us 2 square root c over m absolute value sine ka over 2. In the limit k goes to 0, you have sine theta becoming theta. So sine ka over 2 becomes ka over 2. So 2's will cancel and we will find omega is square root c over m capital Ka. So that is our wave vector magnitude. And that basically tells us omega versus k relationship changes, it becomes linear. And the slope is a square root c over m. So if you go back to my plot here, you can see that the slope of this will be, if this is angle theta, tangent theta will be what I find here, a square root c over m. So that will be the slope of this long wavelength limit. So what does that mean? For sound waves, omega is equal to speed of sound times k. So we have a linear relationship. So when the speed of sound is equal to a square root c over m, this is a dispersion relation that is not periodic and it is true for a continuum. So it means that in the long wavelength limit, the sound wave does not see the discreteness of the crystal. So sound waves are in the long wavelength limit and they don't see the discreteness of the crystal. So this is when we get this linear relationship omega and k. And also one important result that I have found is that in the omega versus k relationship there is a maximum omega. So that is here 2 square root c over m. So what does that mean? So what if I try to produce waves with an angular frequency greater than that? This means that only those frequencies in the range 0 to omega max will be transmitted, others are attenuated. So the conclusion is that the crystal acts like a low-pass filter. So it will not allow frequencies greater than omega max to be transmitted. Now in the physical interpretation, in the long wavelength limit, when lambda is much greater than a, if I plot explicitly what the atoms are doing, you can see here I have a long wavelength and the atoms are displaced from their equilibrium positions. The maximum displacement is for this atom. So what I see is that for the neighboring atoms here, they move in phase with each other within this half wavelength. And so that is within a loop, and the restoring force on each atom due to its nearest neighbor is small, therefore omega will be small. So we have a very gradual change of displacements, and therefore if you look at the stretch or compression in the springs that connects these atoms, since the displacement from equilibrium of the spring is small, the restoring force will be small, therefore the angular frequency omega will be small. For maximum omega, for k is equal to 0, lambda is equal to infinity, the whole crystal moves as a rigid body. So the opposite limit will occur when k is equal to pi over a equals 2 pi over lambda, so that's lambda is equal to 2a. So first we talked about the long wavelength limit, so that is k is equal to 0, lambda is equal to infinity. That corresponds to this scenario here. And now for maximum omega, we will have k is equal to pi over a. So if you go back to my plot here, you can see that the maximum occurs at the first Brillouin zone boundaries. Okay, so if I substitute k is equal to pi over a, lambda becomes 2a. So what does that mean? Lambda is equal to 2a. So I see that for lambda to be 2a, the neighboring atoms should be moving out of phase with each other. That will cause the maximum stretch and maximum compression of the spring between them. So the restoring force will be maximum. So that makes a lot of sense. So to summarize, our solution for the normal modes in a one-dimensional monatomic Bravais lattice is a traveling wave solution. It has the form a e to the I k n a minus omega t. K values are discrete such that the phase is increasing from one atom to its neighboring atom. And when we substitute the solution to our equation of motion, we find the oscillatory omega versus k relationship, that is the dispersion relationship. And this suggests that there is a maximum omega when k is equal to pi over a or minus pi over a, and it's 0 when k is equal to 0. And in the long wavelength limit, the relationship becomes linear. And the behavior in the reciprocal lattice is symmetric. So basically we see that reduction to the first Brillouin zone gives us the full picture, because after that it's going to be periodic. And at the first Brillouin zone boundaries, we have standing wave solutions, and that is equivalent to the Bragg reflection of X-rays when theta is equal to pi over 2 and k is equal to pi over a. So that satisfies the von Lau diffraction condition. And that gives us basically standing wave solutions. Now, in order to interpret the long wavelength limit, I substituted for sine ka over 2 ka over 2, and I find the linear relationship, which will be the case for sound waves traveling in the medium, so that's in the continuum limit. So long wavelength sound waves will not see the discreteness of the crystal. And because I have a maximum angular frequency that can be transmitted, the crystal acts like a low-pass filter. And in the long wavelength limit, I see this the small displacements between atoms. So the stretches or compressions of the springs are small. That is long angular frequency limit. And for k is equal to pi over a, I see that the atoms are moving out of phase with each other, with respect to each other, and that is forming the maximum possible compression or stretch in the springs that connect them, and that gives us the maximum possible angular frequency.